Thank you.
So I cut the person who draws all the time.
Who?
This morning. Could you please erase that? She said yes. She said, yes, I'll erase it. So if you missed the art, I'm sorry, I was just like, we need to clean before we get in there. So, and today we'll be wrapping up 4.1, which dealt with those max and mins just over a certain range of values, maybe from x equals -1 to -2, a certain domain. And then we'll jump to 4.2 and actually get to 4.3. So that's what we're doing. 4.1 is still just this idea of we've introduced what are critical points, max and mins, and we get to 4.2 mean value theorem. All right, and then 4.3. Concavity, increasing, decreasing. Relative maximums. We'll hit all those topics. So, but before we wrap up 4.1, does anybody have a question or problem? Cool. 4.1 was neat because you're finding these critical points. It's one of the problems. So that you might find quite interesting. But these, we did find the max and mins. Let's see. Okay, we'll move into 4.2 then. Yeah, 37. But anyone, if you had questions later on from 4.1, let me know. There's some graphs in there, but when you get to 4.3, the graphs return. So I'm gonna wait today until we get to 4.3 before I put the graph down. And we analyze graphs. We'll analyze graphs, first derivative graphs. We'll take that first derivative graph to be able to get an idea of what's going on with the original function. Okay, so recap, critical points. What's the definition of a critical point?
Critical point is that you take the derivative
Good?
and then you enter the points, right, to see if they are over there or not.
That's right, and it's somewhere on this sheet. If you're like, man, what's a critical point? It's just like this stuff has so much information on it. You can look through it and go, where is it? You'll find it somewhere. Do you see it?
Derivative equals 0 or doesn't exist.
There you go. First derivative determines critical points. All right. A critical point is any point in the domain where f prime is equal to 0, f prime does not exist. All right. But also, you know, today, first derivative, as we already know, finds max and mins and intervals of increase and decrease. So when I'm saying we already knew first derivative found the max and mins, we haven't talked about increase and decrease intervals yet. Okay? And so, before we get into some of those problems, because they really come up in 4.3, let's look at 4.2 with the mean value theorem. All right. Enough of that. Sometimes it's nice just to see an image of a graph and then talk our way through it. Understand something like the mean value theorem. F minus 12x plus 3x squared. Cool. if anybody has their textbook, everyone, this is on page 288, 4.2. What's the range of the values going from? 1 to what?
3.
1 to 3. I'm gonna take it from 1 to 5.
Okay.
Cool? I'm gonna go from 1 to 5. And afterwards, we'll back up and do 1 to 3. So this is light, just like number 1. From 4.2. In the textbook. That's on page 288. But we'll look at this function. And we're gonna apply what's called the mean value theorem. And we'll put the mean value theorem on the board, even though I got on that sheet. We'll write it all out, we'll make sense of it. What's that graph look like? I love it, yeah. You got a parabola there, right? And so what's gonna go on with this thing, you're gonna get some kind of parabola. Maybe it's like this. And between these 2 points, let's say here's where x equals 5. And maybe here's where x equals -1. Or excuse me, x equals 1. So it could be different. But this could be any function. What we're saying is, can you imagine the slope of the secant between these points? Wouldn't it look like that?
Mm-hmm.
So just think of this secant right here and think of the slope of that secant. Mean value theorem says this: as long as your function's continuous, all right, as long as it's differentiable and continuous, there's no crazy corners, no breaks, no jumps, but it's nice and smooth like a polynomial, then the mean value theorem states somewhere between x equal to 1 and x equal to 5, there's got to be a point on your curve where the slope of the tangent line of the curve has to be parallel to that secant line.
Gotcha.
This is the mean value theorem. So we'll take this part, we'll make the exact graph, but that's the concept of mean value theorem. You know what's going on? All right, let's say this was x equal to 5. Oh, there it is. And this is x equal to 1 right there.
Mm-hmm.
And that's a secant. And you and I know how to find the slope of a secant. We don't even need calculus. We just do rise over run, true?
Mm-hmm.
Y sub 2 minus y sub 1 over x sub 2 minus x sub 1. All right. As long as this curve is differentiable and continuous on this interval from 1 to 5, then somewhere along the route, somewhere between 1 and 5, and it could happen more than once, but it has to happen at least once. It has to happen at least once. There'll be a point between them where the slope of the tangent line is parallel.
So they both are the same m.
That's exactly right. That would mean they both have the same slopes. So somewhere, when I want to make a line that's parallel to this, it looks decent. And you're like, okay, there's my tangent line. That looks better. There's my tangent. At some point, slope of tangent to curve must equal the slope of the what?
Secant.
Secant.
Mm-hmm.
Now, we can write out this theorem, we can apply this problem, we'll look for that point. I say we find the point. It'll be a point between 1 and 5,
Mm-hmm.
okay? It's gotta happen. It's gotta be at some point between 1 and 5. Maybe it's at x equal to 3. But maybe it's equal to x equal to 3.5 or something. True? Maybe it's exactly halfway. Sometimes it's exactly dead center in the middle where it happens. But it has to happen at least once, and it can happen more than once. It can happen more than once. Okay? So, I think we should write out the mean variable theorem. Well, the beginning part says this: if your function's differentiable and continuous on a to b, then what has to be equal? Let's start with slope of secant. What would be slope of secant? What's the formula for that? Remember, no calculus. Y sub 2 minus y
X
sub
sub
1
one,
over
isn't it?
x sub 2 minus x sub 1?
Yep.
Well, if I call this a and I call this b, I guess I could write that as
F of
f of b minus
F of A.
f of a all over
B minus A.
b minus a. Alright? So we're saying, alright, that slope must be equal to the slope of the tangent
Of the
drawn to
dot.
the curve. And this is going to be real easy to write.
F prime of B minus F prime of A.
Even better, do you agree? How about just f prime?
Yeah, F prime, sorry.
Does that work? But I'm with you. We're like f prime and we're like, at some point, there's got to be some, so we got to make up a letter. Let's use a letter other than A and B. At some letter other than A and B, there's got to be a point between these two right here. 5, be at some point along the way, maybe at 4, maybe at 3, maybe at 3.5, at some value between x equal to 1 and x equal to 5, or x equal to a and x equal to b. So you want to use a C word?
Yep.
So we'll use C. The author does the same thing. All right, here's A, here's B, at some point C. But we got to say C has to be what? Between which letters?
B and A.
There we go. All right, very good.
Okay.
And you'll see it, where is this written, somewhere on here? Do you see it? I got it buried near the bottom though. I want to go way near the bottom of that sheet. So that's what I mean. You want a summary of 4.1 to 4.3? You got it right there. This will hit on everything. It's just all piled into one sheet. So let's try this, someone. You go, what's the question? Can you find the value of C that's between x equal to 1 and x equal to 5? Such that the slope of the secant between 1 and 5 is equal to the slope of the tangent. Let's try that. What would your author say? I know a number. Now look, he has to say numbers, because could there be more than one?
Number.
This one I think you're going to find only one, but there could be more than one, right? Think of curves like sine curves. Or some of the things that go like this. And if you did a tangent, there might be a few places where it's like, right? We can draw some of those. Number 7, I put number 7 for practice. So if anybody has questions on number 7, let me know. I might even put it on the board after we do this problem. All right, final number C. That's satisfied. The mean value theorem. I went for mean value theorem, I'm just gonna put MVT, okay? Mean value.
Is this called the Rolle's theorem?
Oh, you're good. That's coming up.
Okay.
Rolls, it's gonna be very specific. You'll like that.
Yes.
But if you understand mean value theorem, Rolls theorem, you're gonna be like, piece of cake. You're gonna like Rolls theorem. This is mean value theorem, right? Between A and B, there's gotta be some C value where the slope of this tangent equals the slope of the secant. Well, in this problem, we're gonna find that number C. All number C, it satisfied the conclusion of mean value. On the interval, what was the interval?
1 and 5.
And I'll just point like this, on the interval 1 to 5. So I say we start with the easy part. What's the easy part?
Slope of the secant.
Yeah, let's do slope of secant. No calculus, right? Right? F of 5 minus f of 1 all over 5 minus 1. Okay, what's f of 5? This is, y sub 2 minus y sub 1. This is also, by the way, do you remember this? Average rate of change of the function. Remember that from day 1?
Mhm.
That's really what we're doing. This is called average rate of change of the function on the interval 1 to 5. We don't need derivatives, this is what's fine, but it's also slope of the secant curve. Dude curve. Alright,
So f of 5 is
what is f of 5? And by the way, as we're doing this, you might want to help me out, maybe we should make a decent curve. I got
negative,
this image.
negative 30.
F of 5 is negative 30?
Yeah, so 5 squared is 20. Sorry, no, that's 5 squared, sorry. 25 times
Yeah,
3 is
5
7.
minus 60
Plus 7.
5 minus
plus
20.
75. Is that 20?
Yep.
20. Minus throwing, by the way, the curve, you're going to help me build it. Like I said, 1, 2, 3, 4, 5. It got all the way up to what? Way up here. Woo! We knew that's parabola. All right, what's f of 1?
F of 1.
Negative 4? So 20 minus negative 4. So I guess this curve's doing what? Right?
Mm-hmm.
I think it's pretty steep. I think it's pretty steep, but That is a curve, everyone, let me give it a little bend to it. Going up, now, slope of secant, you just gonna get the slope of that, whoa, yellow. What's the slope of this secant? We're finding it right now.
6.
6. So in this straight line, the gradient rises 6 notches for every one notch it runs to the right? Okay. Then put an equal sign, and F prime of X on this side. Wait, I thought we were supposed to put C. You can put C. I'm saying let's just do F prime of X, and at the end we can make it a C. Does that sound good? We're gonna make it C, okay. Then you gotta write it in terms of C, but what's the derivative of that?
Negative 12 plus 6x.
Good job. Derivative of 5 is 0, right? Derivative of negative 12x, negative 12. Derivative of 3x squared, 6x. Right. No chain rule needed, no quotient rule. Nice and simple, huh? But how do you solve this equation?
That equals to 6. The derivative.
6 equals negative 12, whoops, get that x off there, where'd that go? 6 equals negative 12 plus 6x. Now, how do I get that off that side? What's 6 plus 12?
18.
18 equals 6x?
Hmm.
What's x equal to?
3.
And I'm laughing because isn't that dead center between the what?